The next 2 weeks, we will be determining the concentration of zinc in a hair sample by flame atomic absorption spectroscopy. Zinc is an essential trace element, and though we only need a small amount, it is necessary for our bodies to function normally. Because our bodies can't make or store zinc, we must get it routinely from our diet, and it can be obtained by eating meat, fish, nuts, and can be taken as a supplement. Zinc plays an important role in immune function, and from this figure, you can see how having too much or too little zinc can adversely affect our health. Common ways to test for zinc levels include urine and blood tests. We have chosen to make both your and our lives easier by using hair instead. It has previously been shown that the average concentration of zinc in human hair is approximately 200 ppm. Hair is often used for diagnostic tests, the most well-known probably being for drug testing. This is because at the root of your hair, the follicle is connected to arteries in which your blood flows. Small amounts of chemicals found in the blood can get trapped within the hair, which can be detected. Testing for particular compounds can be efficiently done in hair due to the fact that they tend to persist longer in hair than in the body. For example, THC, the active ingredient in marijuana, can only be detected a few days after it has been used in urine, but can be detected up to 90 days after usage in hair. To quantify the amount of zinc in your hair sample, we will be using flame atomic absorption spectroscopy, or flame AA for short. Flame AA is used to determine the concentration of a metal in a sample. These metals include 1A and 2A metals such as sodium, magnesium, potassium, and calcium, as well as those found in the D and P blocks, such as iron, aluminum, platinum, gold, and many more. There are several advantages to flame AA. Being sensitive to others is a trait that I highly admire. I also love when the instruments I'm using are sensitive enough to detect low concentrations, like flame AA. Other advantages of flame AA is that it is relatively inexpensive, fast, and can be used in a high throughput manner. Unfortunately, there are some disadvantages. The first is that large volumes are needed to get good results, and only solutions can be tested. That means no solid or gas samples. In addition, only one element can be analyzed at a time. This figure is called a block diagram. Block diagrams are simplified ways of explaining how instruments work. Almost all instruments used in science can be described in this way. Analytical chemistry is full of them, so try to get used to seeing them now. Light from a radiation source, in our case a hollow cathode lamp, is focused by a lens onto the atomic vapor of the flame. This atomic vapor comes from the sample, which is introduced into the flame via a nebulizer and atomizer. The light given off from the sample is further focused by a second lens and enters a wavelength selector. We are using a monochromator that is tuned to isolate only the light of our wavelength of choice. Our selected wavelength of light goes to a detector, in our case a photomultiplier tube, a PTM, which is able to multiply the signal of the light that hits it. Even an individual photon can be detected. The amplifier further enlarges the signal while decreasing the noise. The signal processing is done by the software, which gives us our data output. We are using a hollow cathode lamp as our radiation source. Here's how it works. First, an electric current is produced between the anode and the cathode, which produces a high-energy plasma from the buffer gas, which is usually neon or argon. Second, the excited buffer gas collides with the cathode, which is made of the metal you're analyzing, knocking some of the metal atoms off of the cathode. These free metal atoms bounce and collide, and the excited buffer gas consumes some of that energy. This puts the metal atom in an excited state. As the excited metal atom relaxes back to the ground state, photons are released, giving off the light as output. A nebulizer is used to inject the liquid sample into the burner. The nebulizer uses compressed gases, in our case a fuel and an oxidant. The high pressure of the gas forces the liquid into an aerosol. This aerosol is then pushed through spoilers and baffles to filter the aerosol to a discrete size of approximately 5 to 10 nanometers. This aerosol can then enter the flame with the fuel and oxidant. After the sample is in an aerosol form, it goes through the burner. The purpose of the burner is to concentrate the solution further, essentially to evaporate the excess water present. As you can see in this figure, the nebulizer creates an aerosol from your liquid sample, which as it goes through the spoiler is condensed into smaller droplets. As the aerosols interact with the flame, the small liquid aerosol droplets change into a gas, which becomes a supersaturated solution. This solid gas aerosol is what produces the absorbance values we are interested in. Flame AA is based on the fact that ground state metals and metalloids can absorb light at a specific wavelength. The Beer-Lambert law shows that there is a linear relationship between absorbance and concentration. This relationship is described using the following variables. A, which is the measured absorbance. Epsilon, written using the Greek letter epsilon, is the extinction coefficient. This value is a constant, which is in units of molar to the -1 times centimeters to the -1. The extinction coefficient expresses how strongly a substance absorbs light at a specific wavelength. So the more light a substance absorbs, the higher the extinction coefficient. B represents the path length of the cell, expressed in centimeters. In our case, the path length is the length of the flame. C is the concentration of the sample in moles per liter. This means that absorbance is a unitless number. Absorbance can also be described by the intensity of the light that remains after some has been absorbed by the sample, divided by the initial light intensity before it hits the sample. Once you have the absorbance value of the zinc in your hair sample, you will determine the concentration using a calibration or standard curve. Because concentration is linearly proportionate to absorbance, we can use standard solutions in which we know the concentration to determine the concentration of zinc in your unknown sample. By plotting the absorbances of your known samples, you can generate a curve expressed by the equation y equals mx plus b, where m is the slope. Given we know the absorbance of our unknown sample, we can plug this value in for y and get our x, or concentration. Hey guys, please pause the video here and write the procedure in your lab notebook. Here's the procedure for the second day of experiment 4. If we have time, we will start doing AA on day 1, so please pause here and write this in your notebook as well. Here's the rest of the procedure for how to do flame AA and what to do with your sample after results have been collected. Please pause here and write this down. For this experiment, you'll be writing a full lab report. Please stop here and record this information. If you have any questions, please contact your TA and ask.